Professor David Wans. David is a professor of cosmology at ICG, the Institute of Cosmology and Gravitation in Portsmouth. He's a leading expert on the physics of the early universe and the origin of cosmic structure, but he also did very important contribution on other topics that include primordial gravitational waves, relativistic effects, and in general, the late-time universe. Today, he will tell us about stochastic inflation and primordial density perturbation. Please, David, the stage is yours.
Thank you very much, and thanks everyone for coming in the morning for the talk as well as your croissants and coffee. Yeah, and especially thank you to Jael, Adam, Julian, and Francesca for inviting me here. It's been nice to spend time talking with people here. And I'm going to tell you a bit about my work today, what I've been doing in recent years, especially studying models of inflation in the very early universe. So theoretical, uncertain, high energy physics models applied to the early universe, but with the hope that we can learn about this very early phase in the universe from the structure, the cosmic structure that we see. So the primordial density perturbations I'm talking about how the dynamics of the very, very early universe, that fraction of a second after the hot Big Bang, generates structure which we see as fluctuations in the primordial plasma in the hot radiation-dominated universe, fluctuations in baryons and photons and things that we see, and in particular that we see through the cosmic anisotropies in the cosmic microwave background. So this is so I'm going to start giving a sort of general discussion about inflation and why I think it's interesting, and hope I can convince you of that too. And then I'll talk more specifically about work that I've done in recent years, studying this, using this stochastic formalism to describe not just small fluctuations, but actually large density perturbations that could be produced in some inflationary models. And so this is work with, most recently with my PhD student, Joe Jackson, and colleagues in Paris and Portsmouth, and in fact, some work with some postdocs, Danilo Artigas, Manu Frion, Thais Miranda from France and Brazil, working in Japan and places at the moment. So that's to come out very soon, I hope. But we'll get to that later. So there will be more technical bits later on in the talk, but I'll start with a sort of general description of how inflation works. And, you know, as I say, this idea of an accelerated expansion in the very early universe is offers the possibility of describing using physics that we can make predictions for what becomes the standard lambda CDM cosmology after inflation. And so inflation really provides these initial conditions for presumably the lambda CDM model, or indeed any other variation on that you wish to study. There's always the question in the standard cosmology of, in the hot Big Bang cosmology, of where do the initial conditions come from? And this accelerated expansion, rapid expansion in the early universe was proposed in order as a way of explaining why we have a very large, homogeneous, isotropic, indeed spatially flat cosmology. But then so it's successful, at least for some, and then people are investigating these days how robust those predictions are when you start with very more generic initial conditions, but at least it's an attractor in some neighborhood to produce this sort of large isotropic spatially flat background. But crucially, it also provides, and it wasn't designed this way, but people realized after inflation was first proposed that it has within it the seeds for producing fluctuations. And so what works spectacularly successfully, I would argue, and why some of us love it, is because it produces this origin automatically gives you some primordial density perturbations, and they turn out to work very well as initial conditions within the standard lambda CDM cosmology. And I want just in very general terms start off with a reminder that it doesn't have to be that way. And if you look back to, I can look back to the 1990s when I started doing research in this field. And there was, at the time, there was a very elegant, simple, and well-motivated model, physical model for the origin of structure that was certainly studied a lot in England and in Switzerland, I think, as well. And that was the idea of spontaneous symmetry breaking at high energies. It's a feature of, in fact, in the standard model of particle physics and Fermi extensions, beyond the standard model, that you'd have spontaneous symmetry breaking at high energies. And if this left topological defects, sort of imperfections in that symmetry breaking in different regions of the universe, you would sort of spontaneously produce a almost scale invariant distribution of structure. And so the classic example would be something like cosmic strings, studied by Tom Kibble in particular in the 1970s. And in the 1990s, the CMB data was something like this. So this is the sort of classic the CL multipoles. So the amplitude of the temperature power, angular power spectrum against the multipole from large angular scales down to sort of degree scales around here, and from balloon experiments in particular that came after the initial COBE, the COBE satellites in the early 90s made the first measurement of the very large scale anisotropies, and balloon experiments were beginning to try and map out the structure at higher multipoles. And the sort of emphasized here, drawn over the prediction of cosmic strings, was that you would get a largely scale invariant with some sort of broad enhancement around the degree scale. And as far as we knew, that was was a perfectly good description of the data, or perhaps it was just beginning perhaps the data was beginning to see this rise in power on the degree scale. And so there were two competing models for the origin of structure: inflation and topological defects. Lots of heated debates about this, but ultimately it's the data that settled the argument. And if we look at the sort of modern angular power spectrum, there's no scope for this sort of broad distribution of power that would have been predicted in the cosmic string models. There is this very strong series of peaks in the angular power spectrum, the baryon acoustic oscillations. They were indeed, Peebles and Zeldovich had sort of predicted the existence of this for adiabatic density perturbations if you had adiabatic density perturbations in the early universe. But inflation gave you a physical description for the origin of these fluctuations, and cosmic strings or other topological defect models just didn't do that. So inflation survived the data, right? And it kind of didn't have to be that way, but the predictions of inflation of almost scale invariant Gaussian adiabatic density perturbations in that primordial plasma seen in the cosmic microwave background sky were all, have all been validated with great precision in the data. The other classic prediction, I think we should add there, is that inflation said that as well as density fluctuations, you would get free fluctuations of the spatial metric. So these are primordial gravitational waves, and they could also show up in the large-scale temperature anisotropies, in particular the B-mode polarization. But so far, we just have upper bounds on this, and I think it remains, a key. If we saw primordial gravitational waves that also had an almost scale invariant spectrum, I think that would be the clinching observational argument for inflation as the origin of these fluctuations. In the meantime, it survives. It provides a good description of the fluctuations we see, and something like topological defects is an elegant, generic physical phenomenon, but it doesn't describe the origin of structure in our universe on the basis of the data. So that's the motivation, I think, for taking inflation seriously. I'll then give you, let me just write down the sort of simple, the simplest model that we discuss when looking at inflation. First of all, driving an accelerated expansion of the universe, and then for studying the fluctuations that will give rise to the primordial density perturbations. So this homogeneous and isotropic expansion can be driven by a simple scalar field. Indeed, in the 1980s, there were no fundamental scalar fields. Now, at least, we know the Higgs field is a fundamental scalar field that exists. It has a potential, a self-interaction potential energy, and that potential energy V is a function of the local value of the field, can drive an accelerated expansion because the field has a potential and kinetic energy that adds to the total energy density, but the potential contributes an effective negative pressure. So if you have a sufficiently slow evolution of the field down its potential, some non-zero, call it false vacuum energy density, gives you an effective fluid with negative pressure. And again, since the 1990s, we've become familiar with that. That's something like a dark energy. But this is dark energy to apply in the early universe. It has to be a very high energy physics. So it's an extension beyond the standard model, but it's an extension at high energies, which is kind of where we expected to find. Perhaps it's more natural to find a vacuum energy density playing a role at high energies. The surprise in the 1990s, as we came into the 2000s, was to realize that this kind of physics seems to be applying at low energies in the universe today. And achieving that at sufficiently low energy scales is one of the challenges of studies of dark energy and trying to understand the present day acceleration of the universe. But as long as the potential is greater than the kinetic energy, twice the kinetic energy, then this the potential energy, vacuum energy, in effect, can drive an accelerated expansion of the universe. That produces this large, sufficient inflation produces a sufficiently large, spatially flat universe, but it also provides the key for generating structure. And that's because if you have an accelerated expansion, then the sort of co-moving Hubble rate, so H is always going to be the Hubble expansion. If I multiply by A, I get a co-moving Hubble rate, which I can compare with the physical wave numbers of fluctuations. So if I've got a wave in my a propagating wave in the scalar field, so we consider also fluctuations, quantum fluctuations indeed, in the scalar field, then because AH is growing with time during inflation, then all modes, it's smaller at early times, right? So all modes actually start on sub-Hubble scales, so we'll call that the ultraviolet small scale regime. And because they start on small scales, we can actually, they're effectively free oscillate. If we just look at a weakly coupled field and look at the free oscillations, the freely propagating modes of the field, then we can quantize them and here we're using a sort of semi-classical approach where we think there's an expanding background geometry, the universe, the space-time we described classically, but then we can study fluctuations on top of that and quantize that. And in inflation, the accelerated expansion means that as AH is increasing in time, modes naturally move from this small scale regime, sub-Hubble, to the super-Hubble regime, where these, what were initially free oscillations of the field, get damped, move into an overdamped regime on large scales. The Hubble damping comes in, you get a squeezed quantum state. And it can be described effectively as a classical random field because of the squeezing of the quantum state. You effectively can describe the properties of the fluctuations just in terms of the the expectation value of the field. But now it's going to be an inhomogeneous field because of the inevitable quantum fluctuations of the free field. And the stochastic inflation picture I'm going to talk about is actually a way to then pick up and study the non-perturbative evolution of the field on large scales, where we work with the large scale field smoothed above some force graining scale. And now the dynamics of a field in a local patch obeys the classical evolution, but also with a stochastic noise that comes from these small scale modes constantly being stretched up and contributing to the large scale fluctuations. And so we can do a sort of nonlinear study of fluctuations, the large scale, the perturbations from inflation using this stochastic picture. The reason we can do things non-perturbatively is that actually we are going to use a small parameter, but the small parameter now is going to be the spatial gradient. And if the spatial gradient becomes small, we can actually locally within this patch, the large scale fluctuation becomes at zeroth order in this gradient expansion. It's just like a local homogeneous universe again within that patch. And in fact, if you think about it, our universe today, we only see a finite patch. When we talk about the background cosmology, we're basically talking about the local average as best we can measure it in our local patch of the universe. And we generally can't know what's on very ultra large scales beyond that, because all we would see is the spatial gradients of that. And inflation, this accelerated expansion just rapidly stretches and stretches and stretches these modes out. So during inflation, this gradient expansion becomes, for a given co-moving scale, becomes better and better and better. Co-moving scales get accelerated up to very large scales, while the Hubble scale actually stays almost constant during inflation. So this is, we can do a non-perturbative expansion, but this is also a way of understanding the standard perturbative, even linear perturbation theory, which is used to describe fluctuations in our universe. Oh, and then I was just going to sort of just note that this is basically, inflation is therefore, in a sense, you flip, the distinguishing feature of accelerated expansion is that you flip around this behavior of waves, co-moving modes moving from the sub-Hubble to the super-Hubble regime. In structure formation, in the non-accelerating universe, matter or radiation-dominated universe, it works the other way around. You always have modes moving from the frozen-in sort of super-Hubble scales down onto the sub-Hubble scales. So when we study structure formation on small scales, we can at late times in a matter or radiation-dominated universe, matter especially, we can basically use Newtonian gravity, and then the large scales are just giving you the initial conditions, right? But in the standard hot Big Bang model, without acceleration, these just have to be given to you with some, initial Gaussian random field. And inflation, because it works the other way, is giving you those in what will become your initial conditions for the large scale structure formation. So now we have quantum fluctuations on top of the classically evolving solutions. So when I talk about the classical slow roll inflation here, I'm really talking about just using how the homogeneous background, sort of reference background that's perfectly homogeneous evolves. Then we get an expansion, and because acceleration is so efficient at expanding the universe, we often work with the logarithm of the scale factor. So n is going to be the log of the scale factor. So the logarithmic expansion is basically the integral of the Hubble rate over time. And in inflation, we can relate that to the evolution of the field from over some field range, sort of sketched out here, from some field value during inflation to the end of inflation. So the duration of n is the duration of inflation. So it's h. We change variables, it becomes h over phi dot times delta phi. And what inflation is doing is these quantum fluctuations during inflation produce perturbations in the duration of inflation in local patches of the universe on the large scale. So our quantum fluctuations delta phi get translated into fluctuations in the local integrated expansion n, and that has a nice interpretation as a curvature. It's a geometric. So these quantum field fluctuations actually produce a curvature perturbation on hypersurfaces at the end of inflation. So it's actually geometry or gravity that links the fluctuations in the scalar field to what will become fluctuations in the baryon photon plasma long after the inflaton field has decayed away into photons, baryons, and standard model particles. So we get from delta phi quantum fluctuations this perturbed curvature perturbation delta n, which is so the local fluctuation in the field gives you a perturbation and expansion h times, you can think of this as delta t, right? Delta phi over phi dot. So basically the amplitude of what will become primordial density perturbations are basically the ratio of this quantum fluctuation to the classical evolution, so dimensionless ratio. And when we see small density perturbations in the large scale anisotropies of the CMB, it's because we've got a largely classical evolution with relatively small quantum fluctuations on top of that. So that's why a perturbative, even a linear perturbation theory description works very well for the cosmic microwave background anisotropies. Okay, so this delta n, or R equal to delta n perturbation from the fields during inflation. Okay, so just to justify that, just note that actually the phase space for a scalar field during inflation is, even with a single scalar field, is two-dimensional, because phi and phi dot are independent. You can think of the initial value of the field, phi and phi dot can be set independently. But what happens in conventional inflation models is this Hubble damping means that there's a rapidly decaying mode, and then there's an attractor solution during inflation, which is what we call slow roll inflation. So these adiabatic perturbations are basically just perturbations forwards or backwards along the slow roll trajectory. And so those fluctuations during inflation map onto adiabatic fluctuations in the photon baryon plasma, where adiabatic here means that precisely this same notion that the fluctuations in local patches of the universe are fluctuations just forwards or backwards along a unique background trajectory. And in a photon baryon plasma, that sort of background trajectory is just it's kind of labeled. It's here, you probably can't see it, but it's basically in the photon to baryon ratio. So adiabatic perturbations along this trajectory don't perturb the photon to baryon ratio. You just have this perturbation in the expansion delta n, which is h times delta t, which is, in terms of the density, it's delta rho over rho dot, or in terms of the pressure, it's delta p over p dot. And although the density and the pressure coming from photons and baryons can be varied independently, you get this specific prediction of adiabatic perturbations, whereas any fluctuations off this background trajectory are what we call non-adiabatic fluctuations, where there's a sort of independent fluctuation in the pressure relative to the density. These are also called entropy perturbations or isocurvature perturbations. And slow roll inflation just produces these adiabatic perturbations. So, and that's what works in terms of describing the initial conditions. The power spectrum, for example, for primordial density perturbations, from vacuum fluctuations, quantum vacuum fluctuations, indeed, in the scalar field during inflation. So I sort of write it as a quantum expectation value for a Bunch-Davies vacuum. You get the power spectrum or the variance for these curvature fluctuations during inflation, and we can identify those with the curvature fluctuations in the plasma after inflation. And indeed, on large scales, the temperature fluctuations in the Sass-Wolf formula on very large scales just gives you that the temperature fluctuations is basically 2/5 times this sort of geometrical perturbation. So when you're looking at the fluctuations of the CMB sky, you're really and in fact, what you see on the large scale variations here is you're really seeing quantum fluctuations at very high energies. That's the claim, of course, from inflation, right? But it's a big claim, but it's a fascinating sort of explanation as to why you see fluctuations here rather than nothing, and why you see these particular type of fluctuations, why you see this sort of 1 degree scale fluctuations in particular with large scale variations on top. Okay. And so, of course, a lot of, and then when we then dig into the details of this, the sort of observational constraints, how you use this, the CMB power spectrum is typically, it's boiled down into just a deviation from scale invariance, which is, a few percent. So n equals 1. Scale invariance that Harrison and Zeldovich, for simplicity, were assuming back in the 70s, lies out here. And what we see is a small deviation from that, which in inflation, it was realized it would naturally occurs from the slow evolution of the scalar field, which gives you a slow evolution of the Hubble rate and the dynamics of the field during inflation. So that gives you, if the slow roll parameters are of order of percent, which there are arguments to expect, then you get a tilt of the order of a few percent, so 0.03. Primordial gravitational waves, well, they are also controlled by the slow roll parameters. And so far, they haven't turned up. So when you plot the constraints, typically you plot the spectral index of the scalar density perturbations here, and have a good measurement of that. I think the fact that it's not scale invariant, that the tilt is a few percent, is good evidence for a slow roll inflation. But we don't see yet those gravitational waves, this tensor to scalar ratio that's used, plotted here. And in fact, the tensor to scalar ratio is basically 16 times the slow roll parameter. I didn't write it in here. So if the tilt is 1%, you might have expected the scalar tensor index to be about 0.1, or even the simplest inflation model, which we still often use as the simple toy model, is with the tensor to scalar ratio would be about 0.15. Unhelpfully, some of the early BICEP results, gosh, is that 10 years ago now? No, maybe not quite 10 years ago, but they discovered precisely this, and were delighted to discover primordial gravitational waves up at this level. But this plot is from the sort of, I think, the latest sort of BICEP, where if you take away the foregrounds, your constraints become tighter and tighter. And now the simple models don't work. There's a new class of models that do work. So they are not the simplest form of models that were being discussed before WMAP, before Planck. But they're perhaps the next to simplest class. I won't get into discussing that so much. And one of the frustrations, I think, for inflation theorists is that the slow roll inflation models, the predictions for the CMB are largely, certainly the ones that seem to be accessible with the current CMB experiments, are boiled down to just 2 numbers. And it is true that there are now many inflation models that you can build models which fit in this data within the slow roll context. So we're very keen to find more information. So
can I
yeah.
question? So what prevents us from lowering more to n?
So what happens is, so the reason n is not, we don't expect so if you had very, very, very slow roll evolution, you drive n towards 1.
Oh, no, I meant the capital N, the folding, the
So the duration of inflation, the amount of expansion. So what prevents it?
Well, it seems to be 50 seems to be closer than 60, and I know we need some inflation, but I don't just put that to 30 or whatever.
For these models, yes. So that varies to some extent with the energy scale that inflation happens. Or the energy scale at which inflation ends. So there's a relation. So of course, what you observe is a fixed co-moving scale. And then you want to relate that back to a particular, and then from your model, you want to relate a physical scale back to a particular value or the amplitude for the fluctuations, a particular value of the scalar field. And so you have to be able to map from that. And so that basically depends on what the physical Hubble scale is at the end of inflation. That depends on the energy scale. And for 30, that energy scale would have to be so low because basically you wouldn't. So this physical scale for fluctuations, you would get maybe fit the data for a given model better down here with a small number of fluctuations. But this physical scale wouldn't be big enough, basically, to map it onto the CMB sky. Because the physical scale that you relate it to is the energy scale at the end of inflation, which is the beginning of the radiation era. And you can't start the radiation era too late. You certainly have to start it before primordial nucleosynthesis, for example. Probably, and then how much before that is, you can argue about. And so 30 would be it's where you map the observables on. So they may appear to fit better here, but you can't basically do it there are constraints so that's actually, reheating. So what you're seeing in this range of predictions for this class of potentials, which the authors, Bicep and Keck, picked out here, are basically simple power law potential models. And so the n is 50 or 60 is basically uncertainty in the duration of reheating. But maybe you can get to 40, but you can't get to 30, which would work there. So one of the big questions about is how you connect the inflaton energy, this field theory, to photons and baryons, the things that we see in the primordial plasma. But actually, because, as I say, I'm trying to emphasize that the fluctuations from inflation, you're really using geometry, these sort of geometrical fluctuations, delta n in this. And although, this physics is very obscure, the idea that it simply perturbs the expansion and then produces a geometrical fluctuation, which is inherited by the photon baryon plasma, is generic and doesn't really care how you convert inflaton energy into baryons and photons. But it naturally gives them an adiabatic case, and the only dependence on the details of reheating is actually what the final temperature is when you start the radiation era, and that gives you this slight uncertainty here in that band here. So it kind of matters. So once you've got a model that sits within this, so it matters in whether your model sits within this band. That's right. So it's an important detail. That is the detail, but it's actually, it doesn't change, that some models basically ruled out of inflation. So inflation, particular models are falsifiable. As I say, the whole concept could be falsifiable if we weren't dealing with an almost scale invariant or adiabatic density perturbations. And now we're ruling out particular classes of models based on the detailed observations of these two numbers. Okay, so I want to say a little bit about going beyond that. There's a lot of, and there are many different directions in which people are trying to find more information about the physics of inflation. You can look for ADAB, and I've tried all of these. You can consider whether you get non-adiabatic fluctuations in the primordial photon baryon plasma. For that, you need additional degrees of freedom during inflation, to be excited during inflation. You can look for deviations from non-Gaussianity, because in there you're beginning to learn about the interactions present between the fields during inflation, which can tell you about, well, interactions are again evidence for additional degrees of freedom. The class, and so typically, but the class I'm sort of going to spend a little bit of time talking about, which I've been working on recently, is still within the single field models of inflation, but where you consider, people have got very interested in studying enhanced density perturbations on small scales. So basically changing the dynamics towards the end of inflation, where we know you must move away from slow roll and to get to the end of inflation. And so this sort of broad class, I'll use the general term of ultra slow roll models for what's going on here, where you get a large, consider whether it's possible to have a large enhancement in the primordial power spectrum. And because the fluctuations that we see as primordial density perturbations are generated from quantum field fluctuations during inflation multiplied by this prefactor h over phi dot, the models we're looking at are models where phi dot basically becomes very small during inflation, hence the term ultra slow roll. And you can do that by basically putting a flat part into your potential. So these are sort of sometimes called inflection point models of inflation. And actually that changes the dynamics from slow roll. You actually break, you can show that to get a rapid enhancement, you actually have to break the slow roll evolution. You move away from having an attractor trajectory during inflation, and that allows you to get a strong enhancement of a sort of rise in the primordial power spectrum, which goes from like k to the fourth. If it's on small scales, it would be washed out in the primordial plasma during the radiation-dominated era, but you might see gravitational relics from this. So this is where people are looking at the possibility of second gravitational waves being induced from these large density fluctuations, pressure waves, and perhaps most speculatively, but intriguingly, the idea of primordial black holes, that you might form black holes, which from large fluctuations in this case. So and we can spend a lot of time discussing primordial black holes because they're a fun concept. Certainly, Stephen Hawking introduced them in the 1970s because he thought, what would happen if, you have black holes that were that small? And in particular, he wanted to see black holes were small enough to see Hawking radiation. If they're very small, they would evaporate. So they're sort of, could be a laboratory for testing quantum gravity if they exist. And so they could form from, but they form only from very large density perturbations in the hot radiation-dominated era after inflation. So delta criticals of order unity, but you can form primordial black holes effectively with almost any mass, because the mass of the black holes are just related to the horizon mass at the time of formation, and these black holes, such large density perturbations, would basically collapse at the time that these fluctuations come back inside the horizon. Remember, the initial conditions set up by inflation re-enter the horizon in the radiation era. And if you have a very large density fluctuation, these are sort of typically the primordial power spectrum is maybe as large as 0.1. So they're on the edge of being perturbative. So that's why it's an excuse for me to sort of look at the effect of non-perturbative descriptions of density perturbations from inflation. And they have to be very rare because they have to be, the abundance has to be less than about 10 to the minus 8 per Hubble volume at the time of formation. So these are, so your typical fluctuation, most of the universe cannot collapse into primordial black holes because then you end up with a matter-dominated universe from high energy scales. So these have to be subdominant and at least until the dark matter begins to play a role, and there are actually constraints even whether they can be a significant fraction of the dark matter. So these are very rare, sort of 1 in a billion or rarer fluctuations that collapse to form black holes. So it's an interesting test case for our study of primordial density perturbations from inflation. So I would argue that the way to study this is to use this stochastic formalism, where we can study nonlinear fluctuations during inflation. So you might worry that I've just said density perturbations of order 1 on super horizon scales. How can this be? How can you possibly study this horribly nonlinear phase? But remember, these scales the density perturbations are on scales much, much larger than the Hubble scale. So the model here is we're using the local dynamics of a homogeneous universe to describe the evolution of the density over in this part of the universe and this part of the universe and this part of the universe. And the inhomogeneity only becomes important, in a sense, once they come back inside causal contact during the radiation era. So during inflation, actually everything's very benign. The density fluctuations during inflation can be quite small. What's going to happen, though, is that the duration of inflation in different patches can become quite large. So instead of the classical evolution or even a perturbative evolution, we now have a sort of quantum diffusion on top of the classical evolution from some initial value during inflation to the end of inflation. So we can still use this idea of delta n as being the primordial density perturbation is going to come from the variation in the duration of inflation in different patches of the universe. But we can use a nonlinear, non-perturbative description of the fluctuations, and indeed even fluctuations on top of fluctuations towards the end of inflation. And then, as we'll see, this can give a very this sort of nonlinearities can give a very non-Gaussian distribution of the fluctuations in the primordial density field. And so you have to modify. So a lot of the results on calculating the abundance of primordial black holes assume a Gaussian distribution, because that's what we always do for primordial density fields. It's very hard to describe the statistics of non-Gaussian fields, but one of the things we've been doing is try to model the abundance of primordial black holes when you're looking at large excursions in the density field, and from a very non-Gaussian distribution at that point. And so this sort of work, which we began in 2017 with my student Chris Patterson, where we were studying this sort of quantum diffusion, and actually we took the limit of a classical phase and then a quantum diffusion on a flat potential. So in a very simple example, we were able to study the sort of probability distribution. So this is the 1-point function, the distribution for the duration of inflation n, and for small, where this quantum phase lasts for a small period, you get effectively from the Gaussian fluctuations of the field, you get a Gaussian fluctuations in the duration of inflation. But there's as you get to larger fluctuations, you also get a highly non-Gaussian tail to the distribution. And what we saw was that you typically get not a Gaussian suppression of the tail of the distribution, but you get a simple exponential suppression. And work by Jose Esquiaga, Juan Garcia Bellido, and Vincent Venin a couple of years later argued that this is a general feature of quantum diffusion in slow roll potentials. So there's an expectation that actually these non-perturbative dynamics will give you very non-Gaussian distributions precisely in the region of fluctuations where you might be, you need to be probing these very large, very rare fluctuations to form primordial black holes. The problem with this work is that it's slow roll effectively. And the models that give you these large enhancements, so to connect while being consistent with small fluctuations on large scales, have to violate slow roll. So a lot of the work recently has been going into understanding stochastic ultra slow roll, where really now we have to look at the full two-dimension, the stochastic fluctuations in a two-dimensional phase space. So we sort of have to look at the evolution, not just of the field, but its momentum. The quantum fluctuations will give you fluctuations in the field and the momentum. But because you've got a squeezed state, you've basically got correlated noise between the field and its momentum. But crucially now, these are not adiabatic fluctuations. So they don't simply take you along a unique trajectory in phase space. So the phase space gets kind of more complicated. So as you roll down from a slow roll phase, large field values, you have a slow roll attractor. But as you roll through a flat part of the potential, you basically get a transient phase here. There's a sudden non-adiabatic transition here. And so although there is a background solution still, the fluctuations during this ultra slow roll phase are no longer squeezed back onto the background. In fact, they evolve along different trajectories in this ultra slow roll phase before, in the simplest model, so we assume it returns to slow roll before ending inflation. So we have to deal with a high dimensional phase space. And there is some debate here, and we'll wrap up, but just advertise to you that there are different opinions about how to deal with this. And I would argue, and you can look at our paper with Joe Jackson, that you can use this rate expansion in the ultra slow roll phase. You just have to work with non-adiabatic noise in the two-dimensional phase space. That's somewhat controversial because traditionally there are arguments that you can't have non-adiabatic perturbations on large scales with a single scalar field during inflation. Going back to sort of classic paper of Salopek and Bond in 1990, where you can look at the sort of, and in particular, you look at what they were looking at is the time evolution of this curvature perturbation R. I don't know if you can see, these are R dots, time derivative of R in single field inflation. If you relate it to the Bardeen potential, this is like the Newtonian potential, but it's really the relativistic version of that. R dot is given by gradient terms, so k squared is the wave number, so k squared times phi. And so if you think the Bardeen, if you work with an expansion on large scales where the Bardeen potential is finite, then this term has to be suppressed in your large scale limit. But that kind of says you live on an attractor on large scales. And we know that doesn't happen on super Hubble scales in ultra slow roll, in the non-slow roll phase. Indeed, we know that R dot does change, and that must be, for a single scalar field, that must be due to a non-adiabatic pressure perturbation on large scales. So, some people, so there's a difference in opinions on how to deal with this. If you want to work with, in terms of the Bardeen potential, you basically have to look at these ultra slow roll phase. You have to include gradient terms. But my argument is that if you work in another gauge, let me jump ahead. We work, the field fluctuations I've talked about are actually calculated in the spatially flat gauge. And there's no such prohibition on non-adiabatic perturbations in the spatially flat gauge. So this is getting a bit technical for the specialists. So let me just say that with our approach, we can now follow fluctuations in what's called a sort of minimal ultra slow roll model. This is a model where you literally add a Gaussian bump onto your standard inflationary potential, and it can be a perturbation of about 1 part in 10 to the -3, but during slow roll, that's enough to disrupt the slow roll evolution. So you get a power spectrum, which indeed is scale invariant and small on large scales, has a big enhancement due to this ultra slow roll phase here. And we can study the 1-point distribution of the density perturbations. And so these are sort of typical fluctuations, 1 or 2 sigma fluctuations, look quite Gaussian. If the solid black curve here is Gaussian, the different colors are different numerical simulations, which look quite consistent there.
So what's the transition scale there? What's the
Yeah, so this is, so basically it's the scale at which the field here crosses it breaks, it goes from slow roll to ultra slow roll. So it's where the potential becomes flat here.
So that's a free parameter.
Yes, yeah, in effect, that's right. So this is a toy model where you put that bump, you move that bump around here.
But if you stay in the ultra slow roll phase too long, then you really increase the e-folding to a large number.
Yes, that's right. So there are problems, and it comes back to this issue of scale as to where you make your CMB predictions. So if I mess around with stuff down here too much, I mess up the mapping between the field value, during inflation and the scale on which the physical scale probed by the CMB sky. That's right. So yeah, so there are practical limitations on how much you can disrupt this for a particular model, or at least it changes the parameter constraints for the inflation model. So having said these are typical fluctuations, I was going to wrap up. Let me just, I just wanted to jump to the work we were doing with Joe, and this is not a picture of Joe Jackson. I couldn't find a picture of my PhD student, but Joe Jackson was a pop star in the 1980s. And looks very cool there, so doesn't look anything like Joe, my PhD student. But Joe's done work sort of numerical modeling into the tail of the distribution, using numerical important sampling techniques to actually sample the tail of the distribution. And so here you really see this big deviation from the Gaussian. If you're down at fluctuations that only occur 1 in a billion or 1 in 100 billion, you're orders of magnitude away now from the Gaussian prediction. The problem is that our modeling, our predictions in different colors here, depend on the details of the modeling. So there are still challenges in getting an unambiguous prediction here. Yeah.
Positive, so it favors positive delta N compared to Gaussian because you have a positive bar, but if you have the negative small bar, would it change sign? I want to set the sign of this delta N.
Yeah, that's right. So it matters because you only form primordial black holes from overdensities, not underdensities. That's right. And so that's why I'm showing you the overdensities, positive delta N here. The Gaussian would be nice and symmetric. These ones are not symmetric. We tend to see enhancements. So I think that's a generic feature really regardless of the shape of the bump, but I don't think anyone studied it well enough to, but yeah. Right, I should wrap up. I say there are many different viewpoints. I've given a scorecard for my colleagues elsewhere, different approaches. I think you can get it wrong, but people have, like, say, Paul Sherrard and collaborators in Cambridge are doing a numerical relativity approach, including the gradient terms. So to me, that's just too hard. But it's too hard to model a billion simulations to find the 1 in a billion events is the trouble if it becomes too numerically complex. Some people want to do a classical expansion rather than the full stochastic work, which is not wrong, but it's not the whole story, I think. And so, of course, I think what we're doing is the best approach so far. But that's my scorecard. Okay. Maybe I should just finish on the general point about inflation. But what I feel confident justifying is that, simple inflation models are consistent with observations, and it didn't have to be that way. But we are still seeking more information, that could come, obviously, from STEMB. Obviously, a big question is whether large-scale structure could extend the range of scales that we're probing with inflation, and whether gravitational relics could give us information about later stages during inflation. And actually, even with fairly small modifications beyond the simplest models, we can get rich phenomenology that I think is interesting to investigate. So I shall wrap up there. Well, I hope there's time for a few questions. Yeah.
Thanks a lot, David. Questions for the speaker? No, and we maybe start.
Yeah.
There is someone there.
Yeah,
so-
yeah.
So I have a question on primordial black holes. So would the collapse of the primordial black holes when they form generate gravitational wave? If there is more particle.
Yeah, so that's right. So they do. Yes, they do. That's right. So if you've got large pressure put, so these are typically forming in the radiation era. So to form a primordial black hole in the relativistic plasma, you really got to crash a large perturbation in on itself. And those kind of large pressure waves in the plasma are exactly what generates gravitational waves. On the other hand, the only thing I'd say is that primordial black holes actually, I remember, only form in sort of less than 1 in a billion patches of the universe. So actually, most of the gravitational waves you would see don't come from those rare events, I think. I would expect them to come from the other more typical, still pretty large fluctuations, but they sort of come from typical fluctuations, and that's kind of, so it's, if you look at the sort of probability here, they're in the sort of 10% sort of 1% sort of fluctuations. Those will be giving gravitational waves and washing out, not collapsing to form primordial black holes. These ones, form primordial black holes, are so rare that they're not the ones you see. And so one of my conclusions actually about, so the link between the two is fascinating, and because after all, primordial black holes are going to be hard to persuade people they really exist. But if you could see an associated gravitational wave background, that'd be really interesting. The trouble is, I think the primordial black holes are just much harder to model. And as I say, I'm not sure there are any entirely reliable calculation of the abundance of black holes for a given, which would correspond to a given gravitational wave background. So they'd exist at the same scale, but the sort of detailed link, so therefore ruling out models based on one or the other, I wouldn't do that yet. Because pulsar timing array sort of gravitational wave background has been used. Some people have said, it can't be induced scalar gravitational waves from these kind of effects because that would be ruled out by primordial black hole abundance. But I'm not sure we really understand the associated abundance of primordial black holes well enough yet to do that.
I want to ask, what are the reasonable ways we can expect to observe a primordial gravitational wave? How do we observe primordial gravitational waves?
Yeah, so there's different ways depending on the scale. So if they're as large as large-scale structure or larger, then if they're 1,000 megaparsecs wavelength, we're not going to measure them with a detector on Earth or even in the solar system. But they produce polarized, but they do affect the propagation of CMB photons. In fact, they can affect the polarization. So they do give an average temperature fluctuation, but the constraints now really come from the particular polarization mode, the B mode on large scales. And that's what the Keck and BICEP ground-based CMB detectors are looking for. So they are squeezing down. So Planck, the Planck satellite gave a bound on the tensor to scalar ratio up here somewhere. Well, that's what the green one is. That's it. There we go. Planck up here in green. But now with ground-based detectors looking for B mode which are designed to look for B mode polarization, the Planck satellite wasn't. They've squeezed it down to this blue region here, and they'll keep squeezing. And it's kind of the next simplest models kind of do make predictions in here. They're sort of potentially within reach of the next generation CMB detectors. That said, you can also get these induced gravitational waves could be much smaller. They could be primordial gravitational waves that would contribute to a stochastic background in pulsar timing arrays data, or if they're smaller, they could even in principle, they could be detected by LIGO if they're on that sort of kilometer wavelength.
And this is including the redshift they will have. Yeah,
that's right. So you sort of calculate how they're generated, well, either during inflation or in the radiation era after inflation. But the radiation era covers a range of scales they'd be generated at. And yeah, so again, you can predict a wide range of scales from these models. And one of the weaknesses, I suppose, is you don't know which particular scale to look at because inflation covers all of these scales.
Just a very short question. Is this a hint of a first detection of 0.7 sigma? Or?
I'm certainly not. It might well be the priors here because you definitely don't go below 0. So it might just be where your priors are. So I'm not. Yeah. I made the mistake of I confess that when the bicep results came out, I gave interviews saying how exciting it was if we could see primordial gravitational waves. I think I said if. Yeah, and I don't think anyone's claiming detection evidence yet.
I just had a simple question, so maybe you can help me understand a bit better why when you change from slow roll to ultra slow roll, why you are then no longer attracted here.
Yes, let me jump ahead to the thousands of other slides that I could show. So I didn't go into this sort of detail, but there are sort of there's two very simple regimes you can be in. So what I actually didn't write down the Klein-Gordon equation. This is how a scalar field, the acceleration of a scalar field evolves in cosmology. So here's a Hubble damping term and a potential driven by the gradient of the potential. And slow roll is the classic approximation is to take a quasi-equilibrium solution here. So damping drives you down to sort of quasi-equilibrium between the friction and the driving term. So instead of a second order system, you've got a first order system, and so there's one trajectory. But ultra slow roll is the limit where you neglect the gradient, the driving term. So it's actually just a transient. So usually you'd think of it as we've always discarded it really as a transient evolution, but it's really a second order solution. So yes, no, you don't. There are two constants here. You don't see it, but of course there's a constant of integration here. So it's really got it's a two-dimensional in the phase space, which I didn't, may or may not have been clear from the complicated. There's a bit of the phase space where you're not necessarily getting squeezed onto this trajectory.
So it happens because the acceleration term is like the term becomes larger than the slope.
Yeah, that's right. And it's it tends to be transient because if phi dot decays is basically being rapidly damped, and then of course if it becomes too small, then you can't say that any finite gradient is going to become important again. So often these are quite short-lived phases, but they're enough to produce large enhancements in the density perturbation, even small phases.
Any last question from the speaker?
And also, more general question. So, are there any viable alternatives?
Yes, yeah. Well, is Robert Brandenburger here? I don't think there are any that are really that I understand consistently. Now, maybe that's my limitation because this is a semi-classical approach where you're well below the Planck scale. So you are doing the quantum fluctuations, but on top of on a classical background, it's an effective theory description. Typically, something like inflation could happen in a collapse model, and I've studied, and you can study these kind of quantum fluctuations in a collapsing cosmology, and there are they can share some of the properties here. The problem with collapse models in general relativity is they collapse and they don't stop. So string theory, quantum gravity, maybe you can regularize these, but you rely on an understanding of the Planck scale, or at least solving that problem. And you've got so basically you've still got a singularity, and now so inflation, you can argue, still has a singularity, but it's in the past. It's before inflation happened, and inflation to some extent makes you less sensitive to the physics of that by pushing it to scales that presumably unobservable. But the alternatives tend to have singularities sitting in them after perturbations are generated, and so that could be that this sort of process could operate there, and there's some, but it relies, but we don't understand. Generally, we don't understand those kind of things that are really non-perturbative or indeed singular. You know, singular means you don't know what you get out from what you put in. That's what a singularity really is in physics, and so that's a problem for most of those models. Well, I think all the alternatives. Almost by, I mean, yeah. So that's why I think inflation is the best framework we have at the moment.
Any other question? If not, let's thank the speaker again.